So let's see if we can do this problem. Oh, by the way, I didn't write it down yet, but we have a dead uniform load and a live load. So we're going to have a dead load of 400 pounds per foot. And that's a dead load. And we'll have a live load of, am I reading the right thing?
It's got a uniform live load.
Oh, it's got a uniform live load. So then we'll have how much was that one? 2 kips per foot. So we got another one that's 2 kips per foot, and that's live. And then on top of that, we've got an 8 kip live load. So these are distributed loads, so they'll be handled a little bit differently than the point load, and we'll get to that. So starting with A, let's see if we can find the reaction at A due to that system. So remember the way Mueller-Breslau works is I would come to A and imagine that structure doesn't have a reaction at A. But what I'll do in its place to kind of visualize it is I will apply the reaction at A. So how is that structure going to behave? Well, this end is fixed, so it's not going to move at all. This is not able to rotate up or down, so it's going to stay there. But about this hinge, this other segment can move either up or down. Now, if I push on it up, which way is it going to go? Up or down? It's going to go up. So the shape of the line, the influence line, should look something like that. So if we want to quantify that and get all the bits and pieces, I'm now going to draw my influence line for the reaction at A across the whole structure. So there's the end, there's the pin, there's my reaction. I know the shape looks like that. So what are the values? Well, what would be the reaction at A, and we're doing the influence line for the reaction at A, when the unit load is right over A? It's going to be 1. Yeah. So that value right there is 1. Now remember, this is 15 feet, this is 10 feet, and this is 10 feet. So we can use similar triangles that says if it's a height of 1 here at 10 feet, what would be the height at 20 feet? 2. So there's my influence line. That makes sense?
So it's 1 at RA because there's the total displacement has to be.
Well, let me draw it a different way. Maybe you can see it better. So if I redraw the problem, why do I know it's 1 there? Well, that means it's 1 there because when my unit load is there, what is the reaction at A? Well, you can see if you sum moments about this pin, they're equal. So if this is 1, this has got to be 1. You can also see is that if it moves to the left and sits out here on the edge, which would be this point, the reaction would have to increase. And if you actually look at the numbers, you would see that in this case it would double, going from 10 then to 20. So that translates into the value right there. So now if this is the influence line, how do we solve the problem? Well, let's start first with the uniform load. So I'll write those here to the side. So we'll start first with the dead load. Now the dead load, do we have any control over where it goes? No, it's over the whole structure. In this case, the whole structure is just, influence line is just this first 20 feet, and it's always positive. So there's not going to be any really decision to make. I just need the area of that particular part. So I know my dead load, since everything else is in kips, I'm going to convert this to kips. So my dead load is going to be 0.4 kips per foot. And then times the area of this curve. It's a triangle. So we know what the area of a triangle is 1/2 the base. The base is 20 feet times the height, which is 2. Well, conveniently, the 2's cancel, and I've got 20 times 0.4, which is 8. Right? So this just becomes 8 kips. So that's the component to the reaction at A just to the dead load. Now we'll do the live uniform load. Now all uniform loads are multiplied by the area under the curve. Now in this case, where do I put my live load? Do I put it over the whole structure? But it really doesn't matter. I definitely need to put it over this area of the beam to get the full effect. In this case, it's the same area. So my live will be 2 kips per foot times the area of the curve, which is again 1/2 base, 20 feet, times height, which is 2. So those cancel, we get 20 times 2, that you get 40. And then finally, the live force, or the point load, we're going to multiply that value, which is 8 kips, times what? What's the maximum value here? 2. And that gives me 16 kips. So the total, the reaction at A, is going to be all these added together. So 8 plus 40 is 48, 58, 64. So 64 kips. Now, what does that look like? Well, if I redraw the beam, and remember the thing we're looking for is this reaction at A. Well, what do I get? Well, if I take my dead load, it has to go over the whole structure. I'll take my live load. It does not. It only has to go over this part of the structure, because that's the only part that it makes contribution to. And then the point load, where does it go? It goes all the way here on the edge, where it creates the maximum value. So that's the configuration that creates the largest reaction at A for this combination of dead loads, live and dead uniform loads and a live point load. Is that okay?
You want us to draw that class diagram on the exam?
No, I like to do that just to help you visualize what it is you're doing. All I'm going to care about on the exam is that you get 64. So what if we do this again, except we'll go for part A, which wants to know the shear just to the right of A. So what I need to do, get another piece of paper here in my stack. I'll kind of cheat a bit. I'll just lay this over the top so I won't have to redraw this stuff. And we'll add the shear to it. Okay. So part B is the shear at A, but it wants the shear at A just to the right of A. So it says? So that's just to this side. This one's a little tricky. Did I point to the left? Okay, just to the right of A. So what that means is right just to the right of A, I have to imagine my shearless connector. All right. So let me draw that. So I'm going to come to A. In fact, I'm going to make it a little more to the right so you can kind of see it. So there's my shearless connector just to the right of A, and then there's B, and then over here to the fixed connection at C. And of course, that is a roller. So now if you look carefully and you apply positive shear to both bits, how is that going to move? I think the easiest one to see is this little segment here from A to B. If I push up here, this point goes up and hinges about B, and you get something that looks like that. Now here's the one that's a little harder to visualize. If I push down on this right side, what happens? It's a little tiny seesaw. So if I push down on this right side, what happens to this edge here? Does it go up or down? It goes up. You get something that looks like that. Kind of a sawtooth. You guys see that? That's kind of an interesting one. So now if I redraw the diagram for the shear at B, and just to the right, I'll call that the positive side on the right side. Then we get something that looks like this. Hey! Hang on a second. All right, I'm going to take a break. E.T. must phone home.